Hi everyone, this is Aditya Anand from University of Michigan, and I'm going to be talking about approximating small sparse cuts. This is joint work with Uyung Lee, Jason Lee, and Tachupon Sarnara. So let's get started. First, let me define the sparsest cut problem. Given a cut in a graph, the sparsity of the cut is basically the number of edges cut divided by the number of vertices on the smaller side. So in this case, the sparsity of this cut is k divided by the number of vertices on the smaller side. So k divided by size of S. And the sparsest cut problem basically asks to find a cut with minimum sparsity. And basically the idea of this ratio objective is to model the fact that we want to cut very few edges while disconnecting a significant part of the graph. And sparsest cut has been a central problem. It has had applications in so many areas. Let me briefly talk about some of them. In approximation algorithms, it's been used to approximate problems such as minimum linear arrangement, cut width. In hardness of approximation, small set expansion, which is close to sparsest cut, is a very important problem with connections to the unique games conjecture. And algorithmically speaking, probably expanded decomposition is the most important application of sparsest cut with almost linear time algorithms for many problems being obtained from expanded decomposition. Graph specification is another application. And tree flow sparsifiers is yet another application in graph theory, where these are really powerful objects that help us approximate many cut problems and also solve the problem of oblivious routing. So it's a very important problem, sparsest cut. And let me briefly mention that most of the fast algorithms for sparsest cut came from the cut matching game introduced by Khandekar, Rao, and Vazirani in 2006. And they form the basis for expanded decomposition and tree flow sparsifiers. Many of these applications where fast algorithms are needed. We'll talk more about this as we get into our problem. So what is known about approximating sparsest cut? So there's a long line of work. Layton and Rao initially initiated the study of this problem with a log n approximation. Arora, Rao, and Vazirani then brought this approximation down to square root log n in their seminal work. And today that stands as the best known approximation for this problem. And in terms of fast algorithms, the cut matching game was introduced by Khandekar, Rao, and Vazirani. They gave a log square n approximation, and the runtime of their algorithm was only polylogarithmically many max plus. It was later improved to log n by Orecchia, Schulman, Vishnoi, and Vazirani. And another version of the cut matching game was also introduced by Khandekar, Cote, Orecchia, and Vishnoi. In fact, that's the version which we will be using. Now let me talk about what our problem is. So we consider the problem of approximating small sparse cuts. So the idea behind this was basically from the thought experiment, suppose the sparsest cut cuts only a few edges. Then can we improve the approximation factor significantly compared to the square root log n? So if k is actually pretty small, can we get a good approximation? And it's also partly inspired by the balance separator problem, because Feige, Hajiagai, and Lee showed in 2005 that actually you can get a square root log k approximation for balance separator when k is the size of the optimal cut. So is such a similar result possible for sparsest cut? So our problem is basically, can you get an f of k approximation for sparsest cut? And f of k is something that depends only on k. So this is a parametric approximation in some sense. And it's similar in spirit to the fixed parameter tractability, where we want an algorithm running in time, function of k times poly n. Here, however, the difference is that we want to allow algorithms running only in polynomial time, but the approximation ratio can depend only on k. So let me state our problem formally and describe what we want to do. So there are two versions. The first version I call the weak version. Basically, this is the sparsest cut problem that I just mentioned. Given that there is a phi sparse cut that cuts only k edges, can you find a phi f of k sparse cut some function? And a stronger version is, given that there is a phi sparse cut that cuts k edges and is of size s, we want to find a cut with comparable sparsity, but also the size should be at most some constant times s. Okay, so this is a much stronger problem. So we want to find a cut that really looks like this. This is basically the algorithmic version of small set expansion. So we call this small set expansion. So these are our two central problems, and one can define a vertex version for both these problems. Vertex sparse cut, where you cut k vertices, and small set vertex expansion. Again, with the hard constraint, with the constraint on the set size. So these are our four problems, and this is what we try to solve. And one other inspiration and also for this problem was that fixed parameter tractability already gives us some approximation like this. So Sigan et al. Showed in 2020 that if there is a set S which cuts only k edges, we can find a set with the same size S cutting at most k edges into the k log k times poly n. So if k is actually quite small, something like log n over log n, then we can solve the sparsest cut problem exactly in polynomial. And if k is actually bigger than log n over log n, then if you look at square root log n, that is actually at most square root k, roughly. So already we obtain a roughly square root k approximation just by using an FPT algorithm. But there is no reason to believe that this is actually optimal. So can we get a polylog k approximation? So that's yet another motivation for our question. So now let me describe our results. First, we show that small set expansion has a log k polytime approximation. This in turn implies a result, the same result for sparse cut because it's just an easier problem. And for vertex sparse cut, we give a log k plus log n phi approximation, where phi is the optimal sparsity of a vertex cut. And basically log n phi is just a small overhead here, but we don't know if it can be removed. And for small set vertex expansion, we show that it's actually much, much harder. We show that it's n to the epsilon hard for some epsilon greater than 0 to approximate. And it's also 2 to the little of k approximation hard, even when we allow algorithms which can run in times fk times poly n. So it's a very hard problem. Finally, we also match our 2 to the k lower bound with 2 to the k upper bound. And the runtime is fk times poly n. Those are our results, and that's one set of results. And the second set of results is basically almost linear time algorithms. We give a log square k approximation for sparse cut in almost linear time, and a log square k plus log square log n phi algorithm for vertex sparse cut in almost linear time. So now let me talk briefly about our techniques. So let me focus on these two results, the polynomial time algorithm for small set expansion and the fast algorithm for sparse cut. Basically, we introduced two techniques. One is that of one is an extension of the sample set technique from the previous paper by Feige and Mahdian. And the other is a new cut matching game for small set expanders. Then we also extend some existing LP rounding schemes. So these are our three tools. The polytime algorithms come from the LP together with sample sets. And the fast algorithms come from the new cut matching game together with with sample sets. So let me go over these two important techniques, the small sets, the sample sets, and the new cut matching game that we developed. I will not say how we apply these techniques to our problem, but I'll just introduce the technique and say how we improve it and what was already known. So let's start with sample sets. What are sample sets? Given a graph, we want to choose some vertices as terminals T. What's the goal? The goal is that for every set whose cut size is at most k, we want the terminals to be in proportion to the set size. So if you have a set whose size is b times n and the cut size is at most k, the number of terminals here should be roughly b times t. We are allowed to tolerate an additive error of epsilon times t. And once I describe this problem, the simplest solution that you might think of is to use random sampling. Okay. How to get such a terminal set? Just use some random sampling. But then the question is, okay, how large is the sample set? Turns out that if you sample something like 10k log n or epsilon square terminals, you can actually accomplish this. You can hit every set with a small cut size in proportion to its size with small additive error. Let's see why. Suppose you have a set whose size is b times n. Then the number of terminals here will be roughly 10bk log n over epsilon square. Okay. But we can actually ensure that the additive error is at most epsilon times t, and the probability of this will be at most, the probability that this is not the case, that the number of terminals is outside this range, is at most e to the minus k log n. Okay, this is simple. This is just from a simple application of Chernoff, because the concentration generally depends on the mean, and the mean here is roughly around k log n. So that gives the probability of this happening, the probability of violating this condition as something like n to the minus 3k. But the number of cuts of size k is at most n to the 2k. So applying a union bond, we get that these many terminals are sufficient. But what is interesting is that Feige and Mahdian showed that there is actually a deterministic algorithm to choose k over epsilon square vertices, such that for every k-sized edge cut with b and vertices, we have the property that we wanted. So there is no need for k log n or epsilon square vertices. There is a smarter way to show only k over epsilon square vertices. So log n is unnecessary. And they use their sample sets to good effect with many applications. They showed FPT and approximation algorithms for balance separator problems. So, and also they showed something similar for detection sets, which were also introduced by Kleinberg. And they are related to network failure problems. So sample sets and detection sets, they have a lot of applications. However, even though this result seems quite powerful, there is one drawback. The drawback is that this is only useful when b is a constant. If b is not a constant, then basically the additive error of epsilon is too costly. It doesn't allow us to say anything meaningful. So for a set whose size is something like square root n, we're not saying something very useful. Here is where our extension comes into play. What we show is that the algorithm in Feige-Mahdian is actually much stronger. It preserves not just the balance cuts of small size, but it can actually preserve all sparse cuts multiplicatively. Formally, what you can show is that if you choose n5 over epsilon square vertices as terminals, then not just balance cuts, you can preserve every phi sparse cut, and not just additively, you can preserve it with multiplicative error. So small sets now also get preserved with small multiplicative error. And that is the advantage of our extension. We are now able to use this for even small sets in a meaningful way. That allows us to get the approximation for small set expansion. Also, we show similar results for vertex cuts, but there actually the log n5 factor is unavoidable. And we show that for sample set, this is actually tight. And this is the reason why we pay the additional log n5 term, if you remember from our results. So that's it about sample sets. Let me talk briefly about cut matching game for small set expanders. Let's start with the general framework of the cut matching game as introduced by Khandekar, Khote, Orekia, and Vishnoi. So first you start with an empty graph. And then there are two players and they take alternate turns. The cut player has to choose a cut in this graph that is of equal size on both sides. So you have to choose a bisection. And then the matching player takes this cut and adds a perfect matching of the vertices across this cut. The matching player can choose any perfect matching between the vertices on the two sides of this cut and add it. Then these matching edges get added to edge. And we repeat. That's how the game proceeds. What is the goal? The goal of the cut player is to make H an expander after log n rounds. No matter what the matching player does, we want to ensure that the final graph that is constructed after log n rounds is an expander. That's the original cut matching game. But what we want in our modified goal is we want to construct small set expanders. So we want to make sure all sets of size S are expanding. We don't want every set to be expanding. But we want to finish much faster. We want to finish only within log S rounds instead of log n rounds. So let's see how to do this. First, let's again look at the cut player of the original cut player in KKOV. Since the goal was to make H expanding, the cut player needs to choose a cut. Cut player simply chooses a cut that is not expanding. So just find a bisection that is not expanding, has less than n over 100 edges, and output the bisection. Okay. So here n is the number of vertices. And potential function analysis shows that you can't proceed for more than log n rounds. So in every iteration, cut player just finds a sparse cut, outputs it. Matching player adds matching across this cut. So at least this cut is fixed, but maybe many others are. What you can show is that this can proceed for at most log n rounds. After that, you will not be able to find a sparse cut, which is balanced. But now again, our goal is to make only small sets expanding, right? So how we'll do this is through a local analysis. Let's fix a set S of size S and see what happens to it as we do the regular cut matching algorithm. So suppose the cut player finds a cut as in the previous algorithm. Let's look at what it does to this set. Suppose this set was cut in an unbalanced fashion so that 60% of S is on the left and 40% of S is on the right. Then we are in very good shape because no matter what matching is added by the matching player, at least 20% of S vertices here on the left will have to be matched outside S in any perfect matching between the left and right. But that means that S is actually expanding after this. So we don't need to worry about this set S after this round. So if this happens for a set, we are in great shape. But this may not happen. The cut that the cut player outputs may actually be quite balanced. Let's say almost 50-50. Then if this is the case, that S is cut in 50-50, now what we want to do is basically try to make this cut, the blue cut, we're going to update this cut and get a similar looking cut, but we want the cut to be sparse inside S. So if you look at these blue edges, we want them not to be too many of them. We want not too many of them to be there. Okay. If that happens, then that's great. So what do I mean by not too many of them? Let's say S over 100. There are less than S over 100 edges here, then it's very good. Why? Because then basically it's as though we were running the cut matching game on this induced subgraph alone. Even though we were running the cut matching game in a global fashion, for this set also we were running a cut matching game indirectly. And that's why we would actually finish in log S. That's the main idea. So the key step here is how to make this cut sparse within S when we might not even know S. You have to make sure that this is true for almost every S. Either you cut it unbalancedly or you cut it balancedly in a sparse way. So we need to see how to update this cut so that it is sparse inside S. So the first thing that we can use to our advantage is that there are not many purple edges. The purple edges are the edges going from S to outside S. Because if there are a lot of purple edges, S is already expanding. So not too many purple edges. But the problem is that there are too many blue edges. So now let's look at this picture again. We have too many blue edges, but very few purple edges. Imagine the flow problem where every edge on this cut sends 1 unit of flow. Okay. Then actually most of this flow from these blue edges, they cannot go out. Because if they try to go out, they have to go through the purple edges, but there are only very few purple edges. Right? So if we want the flow to be feasible, the flow cannot be feasible. The flow will get stuck basically. Now, whenever the flow gets stuck, if we can actually compute a min cut corresponding to that flow problem. So we get a black cut. And then we basically choose this black cut to be a blue cut. And then if you look at this black cut and look at the number of red edges, which are basically the edges on the black cut inside us, there cannot be too many of them. Simply because every red edge here can send flow to the purple edges. So the number of red is at most the number of purple. Right? Of course, we need to set up the flow problem in a more formal way. Honestly, the exact flow problem should be something like each edge sends 1 unit of flow and each vertex absorbs 1 over 100 unit of flow, something like this. But the main idea is simply that since there are too many blue but very few purple, we can actually carry out this update so that the new cut doesn't have too many edges. So let me summarize. We try to run the KKOV cut matching game, but we make sure that progress is made with respect to every set in every round. Either you cut it unbalancedly, make it expanding in this round, or you cut inside it in a balanced and sparse way. And if you do, then that can't happen too many times because you set up this local potential. And the local potential is on S vertices, so it should take only log S rounds to converge. Let me finish by talking about some applications. Algorithmic small set expansion actually has connections to quasi-polynomial kernelization for cut problems. So log K approximation is very meaningful for quasi-polynomial kernelization. This was shown by Wallstrom in 2020. And our results give improved quasi-polynomial kernels for problems including multi-way cut. And we also obtain a log opt approximation for min-max graph partitioning, where opt is the optimal value of the instance. Finally, let me finish with some open problems. First problem is, can we get fast polylog K small set expansion? Parametric approximation for other related problems, f of K approximation. And can we get polylog K approximation for vertex sparse cut, removing this log and phi term? That's another challenge. And finally, the hard open problems, which would be amazing if somebody solves them, are can you improve log and approximation for small set expansion? And can you get a polynomial kernel for multi-way? That's it for this talk. Thank you.